Hello, and welcome to the second recitation on losses. My name is Sri Harsha, and by now you must have known what exactly a loss function does. It provides the signal that for our network to learn based on the training examples it has seen. It is single-handedly responsible for updating the weights or the parameters of our model that dictate its final performance. In this recitation, we will briefly take a look at loss functions for multiple data modalities, such as images, text, and 3D data, and look at some relevant mathematical formulations for the same. Some of them will also be specifically used in your upcoming assignments. Let's start with a popular loss for the object detection task. Single shot object detectors were a huge thing, maybe 8 years ago. There, they would work by predicting hundreds of bounding boxes for a certain image, like we see on the bottom right here. However, all of these 100 bounding boxes would not be of the same dimension. That's to enable the single shot detector to fit a bounding box to images of different sizes or objects of different sizes. A specific size for the horse, another for one human, another for a dog. However, this leads to something known as the class imbalance problem, where you have out of 100 bounding boxes that you're predicting, only 5 to 7 actual objects, and the remaining are classified as the background, which means negative samples where there's no useful signal. And there's only a few positive examples. Until then, literature would use the cross entropy loss to identify if a classification was positive or negative. Uh, Consider the case where we have 100 hard examples and 100,000 easy examples. An example of a hard example would be predicting a horse, and an easy example is predicting the background. Uh, Take a look at how the cross entropy loss varies for the probability of the ground truth class. If the ground truth class is highly likely, the loss is very low, versus if the ground truth class is highly unlikely, the loss is much higher. However, due to the sheer number of easy examples we have, easier examples have a higher probability, the loss contribution from these easy examples significantly outweighs the loss contribution from the harder examples. And thus, this is not a strong enough signal for our network to learn from. In comes the focal loss that introduces a scaling term parameterized by gamma that modifies the contribution of easy and hard examples, uh, the loss contribution of easy and hard examples. For example, if we have the scaling factor to be 1, where the cross entropy loss gives us a loss of 0.1 for a highly likely class, the focal loss only gives that class prediction a loss value of 0.01, thereby reducing its effect on the final loss that you use for backpropagation. Now, this is a reasonable thing to do since in a supervised learning task, which is most of object detection, you usually have a good idea of the probabilities associated with the data distribution. This is just different methods. The authors then experimented with different values of this parameter gamma, and we can see what effect it has on the curves. Therefore, we can deduce that if you want to have the network strictly focus more on the harder examples, you would increase the value of gamma. However, that might lead to uh, poor training or noisy training, given that for most of your ground truth classes, you have a very weak signal. Let's move on to another type of loss, a loss for discriminative embeddings. The one we'll look at is the ArcFace loss. Say we've trained an AI model to detect human faces, which is something you'll do in homework 2, part 2. How do we make it tell two faces apart without having to retrain the model completely? In comes the ArcFace loss. Let's take a little more of a deeper dive into seeing what this loss does on the loss landscape or the class prediction landscape. The model that has learned to represent features in its embedding space has essentially learned to cluster embeddings to assign certain clusters of embeddings to certain class labels, where each color is a unique face. However, if we use something similarly just as the cosine similarity to know if to understand the relation between f phase 1, phase 2, and phase 3, it may not work well simply because due to the magnitude, f1 and f2 are more similar than f2 and f3. but F2 and F3 belong to the same cluster. So that's exactly the intuition behind ArcFace loss, where using this loss, which has a convoluted mathematical formulation to it, but luckily is abstracted away in libraries that you'll use, instead of having a class boundary that's very discrete, as the softmax does, it enforces a gap between two classes in the embedding space, which is useful if you're trying to differentiate between multiple instances in the same class. Let's move on to another loss. Loss for sequence alignment and decoding. Specifically, the connectionist temporal classification loss, which is also something you'll use in your homeworks. Say you have to solve a video to text task, where your input is our multiple video frames and your output is the text 2025. As you see, we have frames that represent a digit, and you could predict a digit for each frame, but then you'd have to merge together these duplicates. This is what the CTC loss helps us with. It predicts a digit for each frame and then merges them together. You can look at implementations online, and I would encourage you to do so. Let's briefly look at losses for other domains. Let's take a look at a commonly used loss known as the chamfer loss for 3D data. This is useful when dealing with point clouds, where you're taking essentially the L2 loss between two sets of points from two different point clouds, where they may or may not have the same cardinality. So this is useful in point cloud detection classification tasks, where your compared ground truth class might not have the same density as your reference class. Another popular loss used for image segmentation is the dice loss, which is based on the intersection of a union. The intersection of a union is computed as you see on the right, where you do 2 times the overlapping region between the predicted and ground truth masks, which is the nomenclature used in image segmentation, divided by the total area of the predicted and ground truth class. You can see that this has some relation to the F1 score, as it handles class imbalance in a similar fashion to the F1 score. Additionally, a very important function for any loss term to have, or any loss function to have, is that it should be differentiable, which the dice loss is, unlike if we use the IOU directly. Here, a more contemporary task is that of image generation. Some losses that have played a huge role in making it happen are perceptual losses, the KL divergence loss, and the elbow loss. Not to go into too much detail in all of these different losses, although I would encourage you to take a look at them yourselves just to understand their application. Let's briefly talk about the KL divergence loss. In a nutshell, it essentially compares how different two probability distributions are to each other. Say we have distribution 1 and distribution 2, as mentioned on the left. The KL divergence loss is given by the summation term for the discrete probability case and an integral for the continuous probability case. An example is the style transfer task. Say we have these two images here, one that's black and white, one that's color, but we wanted to color them in the style of Vincent van Gogh's Starry Night. We would have one model learn the distribution of RGB values in lots of Vincent van Gogh paintings, then learn the RGB distribution of the input query data set, and then learn a function that can map the RGB distribution from one query set to the samples that you've trained on, which is the Vincent van Gogh Starry Night image. The results of that are what you see on the bottom right. Lastly, let's talk about something even more contemporary, losses for at least one stage of LLMs. As much as I'd love to go into detail about this, in my opinion, the training regime and the loss functions that I use for LLM training are what make one LLM better at a certain task than another. But I can tell you for sure that almost every LLM out there uses something known as reinforcement learning with human feedback, abbreviated to RLHF, in its training pipeline. An LLM essentially is a decoder-only transformer that has autoregressive decoding for multiple timestamps. What that means is it predicts tokens or words causally, one that is one after the other. This is usually an unsupervised task which is pre-trained using a large corpus of data. However, we know that for a specific prompt, an LLM can generate multiple outputs because of the stochasticity in the way it selects its tokens. You might learn more about this when you learn about beam search. But then you can actually have a human that scores and ranks the LLM outputs, and then you train a reward model based on the ranking and scoring of this human annotator. This reward model is then used to artificially rank outputs of the LLM and feed it back as a reward signal to tell the LLM how much a human user or operator might like or dislike their resulting output. Well, that's it for me. I hope that you guys uh, were able to see a little bit more into how losses power different AI tools in not just everyday life, but even in research and beyond. I look forward to seeing all of you in class. Bye bye.